Okay, so welcome. It's the third module. Here we are dealing with the material balance without chemical reactions. So as the name itself suggests, there are no chemical reactions involved in this module. Here we are dealing with the unit operations, the material balance that take place on the unit operations. We know what unit operations are. This unit operations is a basic step in a process that involves physical change or chemical transformation during the process. Okay, so it it includes examples like distillation, evaporation, crystallization, etc. So here we're dealing with those kind of operations. So coming to material balance, its introduction to what a material balance is. The material balance is nothing more than the application of law of conservation of mass. So it's just the application of law of conservation of mass. We know what law of conservation of mass is. It says that the mass can neither be created nor be destroyed. So the basic principle of material balance is the law of conservation of mass. So the here we're dealing with a lot of problems. So in all kind of problems, we have to keep in mind that the basic principle used here is law of conservation of mass. So in all the problems, we should always keep in mind the law of conservation of mass. The material balance is also known as the mass balance. So, okay, now it's a general expression. This equation, this expression is a basic equation that we are used in all kind of problems in this module. Okay, it says that the amount of substance entering the system minus amount of substance leaving the system plus amount of substance generated in the system and again minus amount of substance consumed from the system is equal to the amount of substance accumulated in the system. So, coming to the equation, coming to the explanation for the equation, we can see that the amount of substance entering the system, something has to be entered to the system. Like it is the feed of the system. For taking an example, in the case of a distillation, we have to give the input feed, right? So we have to give the input feed. So that is what is entering to the system, and then again subtracted. There is minus the amount of substance leaving the system, and the product has to leave from the after the distillation. Some product is leaving from the distillation column. So plus amount of substance generated in the system, and during and inside the distillation something is generated, right? And my again minus amount of substance consumed from the system, and from that generation something is consumed. From that feed something is consumed by this distillation column. So we after doing all this, it is equal to the amount of substance accumulated in the system. So something is accumulated in this distillation column. So which equals to the what I've said as earlier. So, but generally we take the amount of substance generated and consumed as zero. So, substituting for the amount of substance generated in the system and the amount of substance consumed from the system as zero, we can finally write the final expression as amount of substance entering the system minus amount of substance leaving the system is equal to the amount of substance accumulated in the system. That is, in short, in very short, it is input minus output is equal to accumulation. So this is the very basic equation of the of this third module that we have that has got a wide range of application in all kinds of problems that we are going to use in this module. So input minus output is equal to accumulation. That means that whatever the feed is being given to the system minus whatever we are getting from the system, that is the product, is equal to the accumulation that is accumulated in the system. And now, before going further deeper into this module, we got to deal with something that is a process. So we have already learned this while we were in the high school. The steady state process, that is, the operating conditions do not change with the time. In the steady state process, the operating conditions do not change with the time. That is like the temperature. Those do not change with time. And in the case of unsteady state process, the operating conditions do change with the time. Like the temperature might change, the pressure might change. So if the operating conditions change, they are the unsteady state process, and if the operating conditions do not change, they are the steady state process. And a batch process and continuous process. A batch process is kind of a unsteady state process, and a continuous process is a kind of steady state process. For all steady state and continuous process, the accumulation is equal to zero, because for all steady state and continuous process, no substance is being accumulated in the system. Whatever we are giving as a feed to the system is being received from the system as the output. So there is no accumulation because the operating conditions are not changing with the time in the case of steady state process, and continuous process is a steady state process. So nothing is being accumulated in the system. So whatever we're giving, we are getting it. So input minus output is equal to zero, which shows that whatever we are giving as a feed, the input to the system is being received as product, the output from the system. So input is equal to the output. That is, the input equals the output. That is the basic equation that we are going to use in the steady state process, continuous process. So now it's how to do the material balance problems. So as I already said earlier, this module consists of a lot of problems. How to do the material balance problems? So, an example question is being given in this slide. Soya bean seeds contains 20% oil, 65% inert solids, and 15% water are extracted to get oil. After the extraction, the residue is analyzed to contain 1% oil, 88% inert cake, and 11% H2O. So, what is the percentage of oil recovered from the seeds? So here the feed is a soybean seeds, which contains the oil, inert solids, and water as the amount of concentration being given in the question. And so after the extraction, we know what an extraction is. The oil is being extracted from the soybeans. Okay, and so in the product, it contains 1% oil, 88% inert cake, and 11% H2O. It's not the product; it's the residue, because it's a residue of the soybeans that is being given from the to the input. So what is the percentage of oil recovered from the seeds is the question. So solution. So first step, we have to represent it schematically. So always draw a schematic diagram for the given process. So we can see the feed, which contains 15% water, 20% oil, and 65% inert solids, is being given to the extractor for the extraction, and oil is being extracted, and finally the residue contains 1% oil, 11% H2O, and 88% inert cake. Okay, so this is the schematic diagram of the extraction. Okay, now we're dealing with this problem. Let's study what a key component is. So in most of the problems, there will be a key component. So search for the key components. If the key component is given, it's easier to do the problem. So let's study what a key component is. Components which has not changed throughout the reaction is the key component. Or the not component. So for the key component, there is no change for this component during the entire process. Whatever is being given to the system is being received from the system. So there is no change. Nothing is accumulated, nothing is generated, nothing is consumed in the system for the key component. So whatever we are giving to the feed, we are being received as the product. For in the product, the amount of concentration of the key component in the product and the feed are the same. Okay, so that's the key component. Here in this question, the inert solids are the key component. We can see that the inert component does not take part in any kind of reactions. So the inert solids are the key component in this question. So we know input equal to output. All kinds of process are steady state process unless it is mentioned as an unsteady state process. So here we are taking the equation for the steady state process, that is input equal to output. So the overall material balance is equal to F equal to S plus P. That is, a feed is equal to the product plus the residue. Okay, now now it is a basis is being given as a 100 kg feed. So for all questions, it is first we have learned that we should represent it schematically, and now we should write the basis. The basis means that the basis can be feed or product or anything. Okay, it is a basic step in doing a problem. So first we are just considering it is up to our own opinion to take the base as the product or the feed. It is up to us. So always take it as the question demands. So here the basis is being given as 100 kg of feed. So 100 kg of feed is being given. That means that 100 kg soybean is being given to the extraction. So now the second step is to identify the inert component. So 65% of the 100 kg feed is inert solids. Okay, in the question, it is being given that the 65% of the soybean is inert solids, right? So we know that So now we know that we know what the amount of amount of soybeans is, right? We have taken it as 100 kg of feed. So 100 kg of soybean is given to the extractor for extraction, and the 60% of the soybean is what? It is the inert component. So 65 kg of the feed is inert solids. And since input equal to output, as we have already said, there is no change for the key component. The residue must contain 65 kg of inert solids, since no change happens to the key component. So we are giving 100 kg of soybeans, and it contains 65 kg of the inert solids. So we should receive 65 kg of inert solids from the residue, right? Because the inert solids won't be contained in the oil. It is being contained only in the residue. So 65 kg of inert solids should be contained in the residue. So let R be the amount of residue. Let us consider that the R be the amount of total residue received. So 88% of the residue is inert solids. It is being given in the question. So 88% of the residue is inert solids. We know what the amount of inert solids should be in the residue because it should be as same as it was in the input. So 88% of the residue should be 65 kilogram. And now doing 88 by 100 into R, we equal to 65, equating the equations, we get R equal to 73.86. So that is the amount of so we get R equal to 73.86. That is the 73.86 kilogram. So the amount of residue is 73.86 kilogram. And so we got that the weight of residue is equal to 73.86 kilograms. So now the amount of oil in the input equal to 20% of 100 kilogram, right? We know that the amount of soya being given to the feed is 100 kilogram, and it is being given in the question that the 28% of the feed is the oil. And so 20% of the feed, there is a 20% of the 100 kilogram, that is a 20 kilogram, it is the oil. And the amount of oil in output, now we know what the amount of residue is. It is 73.86 kilogram. And it is being given in the question that 1% of the residue is oil. So equating 1% of 73.86, we get 0.7386 kilogram is equal to the amount of oil in the output. So percentage of recovery of oil equal to. So now our aim is to find the percentage of recovery of oils in the seeds, right? That's what our question was. So now finding the percentage of recovery of soils, we should subtract the amount of oil in the output from the amount of oil in the input divided by the amount of oil in the input into 100, because it should be in the percentage. It should be the percentage. So doing that, the 20 minus 0.7386 by 20 into 100, we get 96.307%. That is 96.307% of the oil is being recovered. Here we have no sufficient data about the oil, so it is better to make the material balance of components other than oil with sufficient data. Just to indicate that we should, if any kind of key component is being given in the question, it is always better to use the material balance or to take the material balance of the component of the key components, because we know that the whatever is being given in the input for the key, as a key component should be received from the product as a key component. So it's better to use the material balance of the key components other than any kind of things. And coming to the unit operations, the first one being discussed here is the distillation. We know what a distillation is. Input is being given to the feed is being given to the distillation column, and the more volatile component is being vaporized, and it is being, and the vapor is being sent to the condenser, and even in the vapor, a little amount of water is being, a little amount of liquid is being contained by the vapor, and it is being sent to again back to the reflux, and the more volatile component or the vapor is being sent as the distillate. It is the products, and from the reflux it is again changed to the vapor, and it goes back to the condenser, and if it again contains any kind of liquid in it, it is being again sent back to the distillation column, and this process continues until the entire product until the vapor contains no amount of liquid in it. So it is the feed, the amount of feed, the amount of the concentration of feed is being denoted as XF. That is the F kilomole per hour, and the amount of product is, there is a distillate is XD, that is a D kilomole per hour, and the residue, that is the bottom product. The top product is a distillate, and the bottom product is the residue. So it is W kilomole per hour, that is the XW. And talking about the overall material balance, it is being given that F equal to D plus W. That is if we, as we have already mentioned, the material balance is based on the law of conservation of mass. That is input minus output is equal to the product. Input minus output is equal to accumulation. Here the input is equal to the feed. So whatever is being given should be whatever is being given to the distillation column should be received from the top product and the bottom products. That is the feed should be F, should be equal to the D plus W. That is distillate product plus residue product. That is the bottom product, and the balance of more volatile component here. Here the F equal to D plus W is the overall material balance, and coming to the balance of the more volatile component, that is we are taking the material balance of the more volatile component. We have to do this. That is the F into XF. That is the amount of feed into the concentration of the feed equal to XD into D plus XW into W. So these are the two equations that should be used in the distillation. There are certain different equations for different unit operations. We should study all of these basic equations, because it is with the help of these equations that we are going to do this all kind of problems. So, and coming to the reflux ratio, it is the amount of liquid reflux by amount of the distillate. It's a very important equation. What a reflex ratio is. Several problems are being done on the basis of, on the based on this reflex ratio. That is R equal to L by D. That is the amount of liquid reflux. That is the amount of liquid being sent back to the distillation column from after the from the condenser, divided by the amount of distillate, that is the top product, is equal to the reflux ratio. Okay, now let's discuss about a problem that, from the distillation, from the unit operation, that is the distillation. An aqueous solution of methanol containing 28% methanol is to be separated into distillate product containing 97% of methanol and the bottom product containing 2% of methanol. For treating 100 kilogram of feed with a reflux ratio of 3.5 on a weight basis, calculate the following: A, amount of distillate and the bottom product; B, the amount of vapor condensed in the condenser per kilogram of distillate; and C is the amount of vapor condensed in the condenser per kilogram of feed. So let's do as we have discussed in the previous slides, how to do the material balance problems. First, represent this one schematically. So this is a distillation process. So the feed, we have taken the basis as the 100 kilogram of feed is being given to the distillation column, and we can see, as we can see, the vapor is being sent out from the distillation column and then sent to the condenser, and some part of it is going back as reflex, and some part is going to the distillate, and we can see the bottom product also. And just remember one thing, that what is the use of reflex? If we are ever hearing this question, what is the use of reflex? The perfect answer for the question is for vapor enrichment. We are doing this reflex for the vapor enrichment, because we are removing all kind of liquids that is being contained by the vapor. So to enhance the vapor, to enrich the vapor, we are using this reflex. So as I have said earlier, we have taken the basis as the 100 kilogram of feed. So F equal to D plus W. That is the equation. That is the first equation that we are using in this distillation process, distillation operation. Okay, and that is the 100 is equal to D plus W. As we are considered that the basis as the 100 kilogram of feed, F equal to 100, right? So substituting for the F equal to 100 in this equation, F equal to D plus W, we can write that 100 is equal to D plus W. That is let's mark it as the first equation. And now coming to the material balance of the more volatile component in the solution, F equal to XD into D plus XWW. And we know what F is. We know what is the value of XF. That is the we are doing this material balance on the basis of more volatile component, right? So it is being given that the aqueous solution of methanol contains 20 weight percentage of methanol. An aqueous solution of methanol, in an aqueous solution of methanol, which one is the more volatile component? Is it the water or is it the methanol? Of course, it is the methanol, right? So the more volatile component is methanol. So we are doing this material balance on the basis of the methanol. So an aqueous solution of methanol containing 20 weight percentage of methanol. So we 20 weight the weight percentage of the methanol is 20 percentage, and so the XF equal to 0.02, right? 0.2. 0.2 is the value of XF, and now we are to do the XD and XW on the basis of methanol, because it is a more volatile component. And it is given that the distillate product, the top product, contains 97 weight percentage methanol. That is, the XD is equal to 0.97, and the bottom product contains 2 weight percentage of methanol. That is, the bottom product contains, that is, the XW contains 0.02. XW is 0.02 and the XD is 0.97, and the XF is equal to 0.2. So we know what F is, we know what is XF is, we know what is XD, and we know what is XW. And now substituting for the equations, we substituting the value for the XF, XD, XW, and F, we get 0.2 into 100 equal to 0.97 into D plus 0.02 into W. And after solving the both equations, that is the F equal to D plus W and the XF is equal to XD into D plus XWW, we get D equal to 18.94 and W is equal to 81.04. That is the amount of top product, that is distillate, is equal to 18.94 kilogram, and the amount of bottom product, that is residue, is equal to 1.62 kilogram. So We know what a reflux ratio is, right? We have already learned it in the previous slides. What is a reflux ratio? It is the amount of liquid. It is the amount of liquid reflux by the amount of the distillate. So R equal to L by D, and it is given that the reflux ratio is equal to 3.5. So substituting for the D and R, we get 3.5 is equal to L by 18.94 and L equal to 66.29. That is the value of L. That is the amount of liquid refluxed. So material balance on the condenser, and we can see that if we are taking the material balance around the portion of the condenser, what is the input for the condenser? It is the vapor that is coming from the distillation column, right? The vapor from the distillation column is the input for the condenser. And what is the output? It is the amount of being liquid being refluxed back to the distillation column and the top product distillate. These two are the outputs from the condenser, and the input is the vapor from the distillation column. So taking material balance at the point of condenser, we get V equal to L plus D. That is, we know what L and D is. That is L equal to 18.94 and D is equal to 60. I'm sorry. We know L is equal to 66.29 and D equal to 18.94. We get V equal to 85.23. That is the amount of vapor equal to 85.23. And in the question, we have to find what is the amount of vapor by per kilogram of distillate. That is a V by D equal to 4.5. And an alternative method is being given to find the amount of vapor by kilogram of distillate. That is, we know V equal to L plus D, and we also know that R equal to L by D, right? So we know that R equal to L by D, so we know what L is. From that equation, R equal to L by D, we can find what is L is. L equal to RD. So substituting for L in the equation for V equal to L plus D, that is V equal to RD plus D, V equal to D into R plus 1. Taking the D as a common from the RD plus D, we can write it as V equal to R, V equal to D into R plus 1. And bringing the D to the LHS, we can write it as V by D equal to R plus 1 equal to 4.5. What we have to find is in this question is what's the amount of vapor per kilogram of distillate. That is the V by D. So we have found it in two ways, that the V by D equal to 4.5. And now to find the now to find the amount of vapor condensed per the kilogram of feed. That is the other part of the question. For 100 kilogram of feed, we have got it as the 18.947 kilogram of distillate. That means for 100 kilogram of feed, we got 18.947 kilogram of top product. That is distillate. So what should be the amount of distillate in the kilogram of distillate for 1 kilogram of feed? It is the amount of kilogram of distillate for 100 kilogram of feed divided by 100, right? So 18.947 divided by 100 is equal to 0.18947 kilogram of distillate for 1 kilogram of feed. So for 1 kilogram of distillate, 4.5 is the amount of vapor condensed. As we have found in the earlier part of this question, for the amount of vapor condensed per kilogram of distillate was 4.5. That is, for 1 kilogram of distillate, 4.5 is the amount of vapor condensed. So what should be the amount of vapor condensed per kilogram of feed? Substituting for all these and finding out the equation, we can write as 1 kilogram of feed, 4.5 into 0.18947 is the amount of vapor condensed. So amount of vapor condensed per kilogram of feed equal to 4.5 into 0.18947 it's equal to 0.8263. And now let's discuss about the next unit operation, which is the mixing. Okay, now coming to the mixing, let's discuss a problem. Let's begin with the problem. 1000 kilogram of mixed acid of composition, 40% of H2SO4, 45% of SNO3, and 15% of water is to be produced. So this is the product. This is the details given are about the products. By strengthening the waste acid of composition, 30% of H2SO4, 36% of HNO3, and 34% of water by weight. So concentrated H2SO4 and concentrated HNO3 are containing 80% are available for this purpose. How many kilograms of spent acid and concentrated acid are to be mixed together? So in the question, it is being given that it is based on the weight percentage. So if in the question it is not mentioned whether it is a weight percentage or whether it is a mole percentage, it is always convenient to assume that it is given as the weight percentage, because it is easier for us to do it in the basis of weight. Okay, so we have learned about how to do a material balance problems. First, represented schematically. It is being represented schematically. Here in this question, the detail about the products is more specific. That is, 1000 kilogram mixed acid is a product. That is what we have to receive in the product side. So let's take the basis as the 1,000 kg of mixed acid, because it is already given that 1,000 kg of mixed acid is being used. So it is better for us to take the basis in the case of product. Okay. Now the feed is 30% of H2SO4, 36% of HNO3, and 34% of H2O. And now let us denote several denotations for the waste acid, concentrated H2SO4 and concentrated HNO3. Let W be the waste acid, and let S kilogram be the concentrated H2SO4, and let N kilogram be the concentrated nitric acid. And now coming to the overall material balance of this equation, it is W plus N plus S is equal to 1,000. Okay, we know we have taken the basis as 1,000 kg of the product. So the we know what W and SNN is. It is the waste acid plus concentrated H2SO4 plus concentrated HNO3 should be equal to the 1,000 kg as it is the amount of product given. So so the overall material balance is equal to W plus S plus N equal to 1,000. That is, the input should be equal to the output. And now taking the component balance, now taking the balance as a component wise. Now let's take the first. Let's take the component balance of the H2SO4. 30% of the waste acid, as we have seen in the question, is H2SO4, and 95% of concentrated H2SO4 is available, and it should be equal to the 40% of the mixed acid. That means 30% of W plus 95% of S plus is equal to the 40% of the mixed acid. That is, the 40% of 1,000 is equal to 400. So 30% of W plus 95% of S is equal to 400. That is 0.3 W plus 0.95 S is equal to 400. That is equation number 2. And now taking the balance of the HNO3, that is 36% of the W plus 80% of N is equal to 450. As it is 450 because 45% of the product is HNO3. And so the 45% of 1,000 kg is the 450. So 0.36 W plus 0.80 N is equal to 450. That is equation number 3. And now taking the balance of the water, it is 34% of W plus 5% of S plus 20% of N is equal to 150. And we can write it as 0.34 W plus 0.05 S plus 0.02 N is equal to 150. And solving the above 4 equations, we will get the answer as W is equal to 70.22 kilogram, S is equal to 398.87 kilogram, and N is equal to 530.89 kilogram. That is waste acid. The amount of waste acid is equal to 70.22 kilogram. The amount of sulfuric acid, H2SO4, is equal to 398.87 kilogram, and the amount of HNO3, the nitric acid, is equal to 530.89 kilogram. So those are to be found on this question, and we have finished this one, the mixing. Okay, now let's move on to the next unit operation. It is evaporation. So as we can see in the diagram, a feed is being given to the evaporator, and we receive 2 products. That is the top product, which is vapor, where no solute is present, and the bottom product, that is a thick liquor L, where solute is present. And so as we have done in the distillation process, the feed is F, and vapor is V, and the thick liquor is the L. So the overall mass balance is F is equal to V plus, and the solute balance is equal to XF into F plus X is equal to XL into L. There is no XV present because no solute is being present in the vapor. Only vapor is being present in the vapor. No kind of solute is being present in the vapor. So we are not taking any kind of XV for this vapor. So that is the overall balance is F equal to V plus L, and the solute balance is equal to XF equal to XL plus XL into L. And that was the case of a single effect evaporator. Now let's discuss about a more complex one, which is the triple effect evaporator. So in this triple effect evaporator, just to simplify it or just to summarize it, it is just 3 single evaporators connected to each other. So at first, to an evaporator, we are giving the feed, and from the feed, the top product, the vapor, is being given out from the evaporator, and the concentrate feed, that the thick liquor, and the other one, the thick liquor, is being given out by the first evaporator, and this concentrate feed, that is the thick liquor from the first evaporator, is being given to the second effect evaporator as the input for the second effect evaporator. Okay, so that the concentrate feed, that is a thick liquor from the first evaporator is being given as input or as feed to the second evaporator, and from the second evaporator again, there might so again the vapor is being taken from the feed and it is being given out, and the concentrate feed, that is again the thick liquor is being given from the second evaporator as the input of feed to third evaporator. And finally, from the third evaporator, the vapor is being given out or is being given as a product, and the concentrator feed, the product is being given out. Okay, so always remember that the concentrate feed or the thick liquor from a evaporator is being given to the nearby evaporator as input or as the feed to the evaporator. Okay, the vapor is being given out, but the concentrated feed, the thick liquor from the nearby evaporator is given to the next evaporator. The concentrate feed from the first evaporator is being given as the input or as the input to the second effective evaporator, and the concentrate feed from the second effective evaporator is being given as the input as the feed to the effective evaporator. So L1 is a thick liquor from the first evaporator, which is the feed to the second effective evaporator, and the L2, that is a thick liquor from the second evaporator, is the feed to the third effective evaporator. So V1, V2, and V3 are the vapors from the respective evaporators, as the name itself suggests. Okay, now discussing about the material balance. Okay, now let's discuss about the material balance of the individual evaporators. Okay, now for the first evaporator, we are giving the feed. The feed is being considered for the first evaporator, and so F is equal to V1 plus L1, whereas V1 is the vapor which is being received from the first evaporator, and L1 is the thick liquor which is being received from the first evaporator. So F is equal to V1 plus L1, which is the overall material balance. And coming to the solute material balance, for the first evaporator, we can see that XF into F is equal to L1 into X1, where XF is the molar flow rate of the feed, and L1 is the flow rate of the thick liquor. And for we are not considering about the V1 because it is in the vapor state. And similarly, for the second and the third evaporator, the overall material balances are L1 equal to V2 plus L2, and L2 is equal to V3 plus L3 respectively for the second and third evaporators. And they come into the solute material balance. It is the L1x1 equal to L2x2 for the second evaporator, and L2x2 is equal to L3x3 for the third evaporator. And if you're adding all the overall material balance equations, we get F equal to L1 plus L2, which is equal to V1 plus L1 plus V2 plus L2 plus V3 plus L3. And we could cancel out the L1 and L2, which is present in both the LHS and RHS. So finally, we get the equation as F equal to V1 plus V2 plus V3. And if we are considering that V1 equal to V2 equal to V3, that is the amount of vapor that we are getting from each evaporator is same, we could write the final result as F equal to 3V plus L3. Okay, so after adding all the overall material balance, we got it as F equal to V1 plus V2 plus V3 plus L3. And if we are considering all the vapors being received from the each evaporators are same, that is V1 equal to V2 equal to V3, we could write the equation finally as F equal to 3V plus L3. So just don't estimate that for all the triple effect evaporators that V1 plus V2 plus V3 is equal. V1 equal to V2 plus V1 equal to V2 plus, I'm sorry. V1, just don't estimate that for all the triple effect evaporators, it is V1 equal to V2 equal to V3. Unless stated, the V1 is different from V2, which is different from V3. If it is stated as V1 equal to V2 equal to V3, we could write F equal to 3V plus L3. Okay, now discussing a problem about this triple effect evaporator. The question is, triple effect evaporator is used to concentrate 100 kg of aqueous solution from a concentration of 20% solute to 80% solute. Assuming an equal amount of vapor in each effect, calculate the composition and weight of the solution and bring the second and third effect. So let's try the solution. That we know what the equations for triple effect evaporators are. That is F equal to L1 plus V, which is the overall material balance for the first evaporator. And we know that L1 is equal to L2 plus V, and we know that L2 is equal to L3 plus V. And finally, we know that F equal to 3V plus L3 because assuming an equal amount of vapor in each effect. So it is stated or it is given in this question that an equal amount of vapor in each effect. So we could write it as F equal to 3V plus L3, where V equal to V1 plus V2 plus V3, and V1 equal to V2 equal to V3. So writing the the molar solute balance for this equation, that is Fxf is equal to L3x3, and we are considering a basis as the 1000 kilogram of feed and F equal to 1000, because we are considering the basis as the 1000 kilogram of feed, so F equal to 1000. And applying a solute balance equation, we could write it as for the Fxf is equal to L3 into x3. We consider the F equal to 1000, so 1000 into 0.2 is equal to L3 into 0.8. So we could, after managing and after calculating these equations, we get the answer as L3 is equal to 250 kilogram. So V is equal to 250 kilogram, and we know that F equal to 3V plus L3. So L1 is equal to 750 kilogram, and L2 is equal to 500 kilogram, and we know that V is equal to 250 kilogram, which is V equal to 250 kilogram. And Fx of physically L1 X1, which is a molar solute balance for the first evaporator. And after calculating everything, we get it as X1 is equal to 0.27 and X2 is equal to 0.405. And so finally, we could write what was asked in the question, that is weight of the solution during the second effect, that is L1, is equal to the 750 kilogram, and the weight of the solution entering the third effect is equal to 500 kilogram. Okay, now it's the next operation, that is absorption. So absorption is very important in the chemical engineering field, as we know what an absorption is. So the gas absorption is an important gas liquid contact operation in which the soluble components of a gas mixture are transferred into a liquid solvent. So absorption always involves an external solvent, and it is used as an industrial separation operation for removal of contaminants, pollutants, and impurities from gases. And for example, ammonia is absorbed from its mixture, producing acetone-free air. In this case, water is used as the solvent because separation is possible since acetone and ammonia are soluble in water and air is relatively insoluble. So, as I mentioned in this slide, what an absorption is, I think you have got the idea what an absorption is. To tell it more briefly, we could discuss an example about the ammonia, absorption of ammonia from the acetone from the ammonia air mixture. So the ammonia is being absorbed from the ammonia air mixture by the help of with the help of water, by using it as a solvent, because the ammonia is relatively soluble in water, whereas the air is not soluble in water. So if you're trying to absorb the ammonia ammonia air mixture into the water, we can see that since the ammonia is more soluble in water than the air is, the more of the ammonia gets attached to the air, and so we could easily absorb the ammonia from the ammonia air mixture, and we could produce the acetone free air. Okay, now let's discuss about the material balance for the absorption system. The overall material balance is given as G1 plus L2 is equal to G2 plus L1, which the amount of substance entering is equal to the amount of substance leaving a system. This is the basis for any kind of material balance. Where let's discuss what G2 and L1 is. G2 is a flow rate of the leaving gas, and L1 is the flow rate of the leaving solvent. So they both are leaving from the system, and G1 is equal to the flow rate of the entering gas, and L2 is equal to the flow rate of the entering solvent. So they are both being entered to the system. So amount of substance entering is equal to the amount of substance leaving a system. Okay, and now coming to the solute balance, G1Y1 plus L2X2 is equal to G2Y2 plus L1X1. We know what kind of solute balance it is. And discussing about a problem on this topic, acetone is recovered from acetone and from an acetone a mixture containing 25% volume acetone by scrubbing with water. Assuming that air is insoluble in water, determine the percentage of acetone in the entering gas that is absorbed if the gas leaving the scrubber analyzes 5% acetone. Okay, so here the solute is acetone, as we know, and as we know what is the procedure for doing a material balance problem. Always first represented schematically. So it is being represented schematically here, and y2 is equal to 0.05 and y1 is equal to 0.25, and we know what a y2 and y1 is. Y1 is the amount of solute in the entering gas, and y2 is the amount of solute in the leaving gas. So here the solute is acetone, and the amount of acetone in the entering gas is 25, because it is given the question as 25% of acetone by scrubbing with water is present in the acetone air mixture. 25% of acetone is present in the acetone air mixture, so 0.25%, 0.25 is y1, and if the gas leaving the scrub analyzes 5% acetone, that is y2 is equal to 0.05. The gas leaving the absorber contains 5% of acetone, that is 0.05. Y2 is equal to 0.05. And G1 plus L2 is equal to G2 plus L1. We know that it is the overall material balance for the absorption. And now here we are taking the basis as 100 kilomole of gas mixture entry, and G1 is equal to 100 kilomole of acetone air mixture. And because it is the input, because it is the flow rate of the entry gas, and G1 Y1 plus L2 by X2 is equal to G2 Y2 plus L1 X1, which is the solid balance for the absorption, and 100 is equal to G2 plus L1 minus L2. Because from the equation 1, because G1 plus L2 is equal to G2 plus L1, so we can write it as G1 is equal to G2 plus L1 minus L2. That is, 100 is equal to G2 plus L1 minus L2, and 25 plus L2 X2 is equal to 0.05 G2 plus L1 X1, which is taken from the equation number 2. And now we are here, and now here we are taking the air, the air balance on the air balance on the case of free of solute. That is insufficient. Here the data is not sufficient for taking the case of solute basis. So we are taking it in the base of free of solute. That is G1 into 1 minus Y1 equal to G2 into 1 minus Y2. So in this base, in this balance, we can see that material balance is based on the free of solute. It is not based on the solute. It is based on the free of solute. So G1 into 1 minus Y1 equal to G2 into 1 minus Y2. So 100 into 1 minus 0.25 is equal to G2 into 1 minus 0.05, where 75 is equal to 0.95 G2, and G2 is equal to 78.947 from the solving. We'll get the answer after solving that equation. And we know that 100 is equal to G2 minus L1 plus L2. So 100 is equal to 78.947 plus L1 minus L2. And we know that L1 minus L2 is equal to 21.053. So the requirements that we asked in the question were is being answered in the answer. Acetone in the entering gas. Acetone in the entering gas is equal to G1 Y1 is equal to 25 kilomole, and acetone in the leaving gas is equal to G2 Y2, that is equal to 3.947 kilomole. So what was asked the question was percentage. What was the percentage of acetone recovered? So percentage of acetone recovered is equal to 5 minus 3.947 divided by 25 into 100, that is 84.212%. So we know how to find the percentage of solid recovered. So that is being done here. Okay. Okay, the next operation is the crystallization. Okay, we have heard a lot about what the crystallization is. Let's see the schematic diagram of the crystallization. The fate is being given to the crystallization, and a little bit of the water is being evaporated, and the crystals are formed, and the and after both the evaporation and the crystal formation of crystals, mother liquor is being given out. So mother liquor plus crystals is equal to magma. That is an important equation for the crystallization. Even though it is not a kind of material balance or anything, it is an important equation to be remembered. Okay, now talking about the overall material balance, we can see it as F equal to E plus M plus C. E is the amount of water evaporated, and M is the amount of magma, and C is the amount of, I'm sorry, M is the amount of mother liquor, and C is the amount of crystals. So F equal to E plus M plus C. And next, coming to the solute balance, we can say it as Fxf is equal to Cxc plus Mxm. And coming to the solvent balance, we know that the relation between the solute and the solvent, it is 1 xm 1 minus x. So coming to the solvent balance, F into 1 minus xf is equal to C into 1 minus xc plus M into 1 minus xm plus E. Since the water is being evaporated, we can see that xc is equal to 0. Now let's discuss a question about this crystallization. Okay, the question is a solution of potassium dichromate in water contains 13% by weight K2CR207, that is potassium dichromate. From 1000 kilogram of the solution, 640 kilogram of water is evaporated. The remaining solution is cooled 293 Kelvin. Calculate the amount and percentage yield of K2CR207 crystals formed. Solubility at 293 Kelvin is 0.39 kilomole per 1000 kilogram of water. Okay, now coming to the solution. Let's do it as we have studied in the procedure for doing the material balance equations questions. First, let's take the base, that is 1000 kilogram of solution. Here we are taking the base as the 1000 kilogram of solutions, and the amount of K2CR207 in the feed is 130 kilogram. because the 13% of 1000 kilogram, as we know, is the 130 kilogram, and the amount of water in the field is 870 kilogram. 1000 minus 130 is equal to 870 kilogram, and the amount of water evaporated is equal to 640 kilogram, and amount of water in magma is equal to 230 kilogram. Okay, and the magma contains K2Cr2O7 crystals and dissolved K2Cr2O7. Okay, so the magma contains both kind of K2Cr2O7. It contains the K2Cr2O7 crystals as well as the dissolved K2Cr2O7. So solubility is the amount of solubility is the amount of K2Cr2O7 dissolved in water. That is what is defined by solubility, which is equal to 0.39 kilomole of K2Cr2O7 divided by 1000 kilogram of water into 230 kilogram, where we get the answer as 26.3718 kilogram, and the amount of K2Cr2O7 crystallized is equal to 103.628. That is, the percentage of yield is equal to 1.103.628 divided by 130 into 100, which is 79.714. So that's all about the crystallization. The next operation is drying. The drying is usually one of the last operations in the process industry. As we know, drying is usually done at the last stages in the industry. They are not usually done at the intermediate stages. In drying, a wet solid or slurry is contacted with the dry gas so that water is vaporized from the solid and is carried away by the gas. Well, we all know this from a practical point of view. At one time of at any point of our life, we might have experienced these kind of things. And the next point is that when the vapor pressure exerted by the moisture in the solid equals the partial pressure of the water in the gas. When the vapor pressure exerted by the moisture in the solid equals the partial pressure of water in the gas exposed to the solid is said to have attained its equilibrium moisture content and drying stops. So when the solid has attained its equilibrium moisture content, the drying stops it. So types of dryers, tray dryers, rotary dryers, freeze dryers, and spray dryers. These are the important types of dryers, and the tray dryers are used for pasty materials and lumpy solids, and rotary dryers are mainly used for granular and free-flowing solids, and freeze dryers are used for foodstuffs and pharmaceuticals, whereas the spray dryers are used for slurries and pastes. And now it's a question on the based on the drying operation. The question is: a dryer is fed with wet solid to reduce the moisture content from 80% to 50%. The product leaving the dryer is admitted to an oven, which further brings down the moisture to 2%. If the dryer can handle 1000 kilogram of wet solid per day, calculate the weight of products leaving the dryer and the oven per day. B, the percentage of original water that is removed in the dryer and the oven. So we can see what all are given in the question. Dryer is fed with the wet solid to reduce the moisture content from 80% to 50%. So the moisture content has been reduced in a material from 80% to 50%. That is the product. That is the material has to be dried. Okay. and now let's take the base as 1000 kilogram per day of feed, and the overall material balance of the dryer is F equal to V1 plus S1. And the moisture free solid balance, as we are done in the absorption solute free balance, we are taking on the base of moisture free solid balance, that is F into 1 minus XF is equal to S into 1 minus X1. So we are taken the F as 1000 into 1 minus 0.8 is equal to S1 into 1 minus 0.15. So after doing the calculations and simplifying the equations, we get the answer as S1 is equal to 200 by 1 minus 0.15, which is equal to 235.294. So the overall material balance for the oven. Now we are considering for the oven. Earlier we had done it for the dryer. The overall material balance for the oven is S1 is equal to V2 plus S2. And so the solid balance, here we are taking on the base of solid balance, not on the, okay, let's do it on the solid balance. That is S1 is into 1 minus X1 is equal to S2 into 1 minus X2. That is 235.294 into 1 minus 0.15 is equal to S2 into 1 minus 0.02. And after calculating and after doing the calculations and simplifying the equations, we finally get the answer S2 is equal to 204.081. And so the weight of the product leaving the dryer per day, that is S1, is equal to 235.294 kilogram per day. And weight of the product leaving the oven per day, that is S2 is equal to 204.081 kilogram per day. So the talking about the amount of water entering the dryer is equal to XF into F. That is XF into 1000. That is 0.8 into 1000 is equal to 800. And the amount of water leaving the dryer is equal to V1, where V1 is equal to 764.706, and water amount of water leaving the oven is equal to V2, and V2 equals 31.213. So the percentage of original water that is removed from in the dryer, V1 by XF into F, the whole into 100 to calculate in the percentage is given as 95.6 percentage, and the percentage of original water that is removed in the oven, that is V2 by XF into F, the whole into 100 is equal to 3.90%. Okay, now we have almost finished our kind of operations. Now we are let's talk about some kind of special operation, that is the bypass, recycle, and purging. So these are very important from the industrial view. Okay, first let's discuss about the bypass. The bypass is employed mainly for affecting relatively small changes in a fluid stream. This is effectively achieved by introducing large changes in a small portion of the original stream and diverting the other portion without passing it through the unit accumulation in this change. The portion so diverted is known as the bypass stream. As we know, what is the meaning of bypass? As we have read a lot about the bypass rods and all in the newspapers, we know what a bypass is. It means that reaching somewhere without touching somewhere. Okay, that is the simple meaning of bypass. Okay, and we can see in this figure that from the gross feed, without going to the process unit, the something is going to the final product, right? So that is bypass. It doesn't touch. It is not touching the process unit. So that is simple meaning of bypass. From the gross feed, something is going to the final product directly without going undergoing the process unit. So the stream that is passed through the process unit is later mixed with the bypass stream to get the final desired change in the combined stream. And the streams A, B, and C have the same composition as well as the other properties. Okay, the next one is a recycle. We all know what a recycle is, and that is what it is doing here. A system with recycle is one in which a stream leaving a processing unit is partly returned to the same unit for reprocessing or reusing. So that's what a recycling is, reusing or reprocessing. So something which is going from a stream is partly returned to the same unit for reprocessing or reusing. That's what a recycling is. We can see the figure. And it is done to increase yields, to increase the purity, to enrich a product, and to conserve heat or to improve operations. So let's take an example. In the fractionating column, a part of the distillate is returned to the column as reflux to enrich the product. That is a drying operation, and the recycled steam combines with the fresh feed A and enters the unit as gross feed C. That is given in this example. And the ratio of the quantity of the substance in the recycled steam to the quantity of the same substance in the fresh feed is known as a recycle ratio, which is quite important in the upcoming semesters. And the overall material balance is net feed material is equal to net product, and once from material balance, the gross feed material is equal to gross product. And now discussing about the questions, and the first question is: the final purification stage in the preparation of certain pharmaceutical product A from natural sources requires centrifuging and continuous filtration as depicted in the figure. Determine the flow rate of the recycled stream in the kilogram per hour. So likewise doing in all kind of material balance problems, first let's take the basis as 100 kilogram per hour of fresh feed, and the overall material balance when the recycled stream is not considered is F plus W is equal to 100, as we can see in the figure. And substituting and we know that overall balance of A is equal to 0.2 into 100 is equal to 0.93 into P, that is P is equal to 21.5 kilogram per hour. And now taking the material balance around the filter, let the flow rate of the product from the centrifuge be as kilogram per hour, and let the flow rate of the recycle from the filter be R kilogram per hour, and S equal to P plus R and S equal to 21.5 plus R. We know what the value of P is. And material balance of A is 0.65 into S is equal to 0.5 divided by 1 plus 0.5, the whole into R, plus 0.93 into P. And after doing the calculations and simplifying the equations, we get the R as 18.7 kilogram per hour. Okay. Now the final topic of this module is the blowdown and the purge. Okay, the major limitation sometimes encountered in the recycling operation is the gradual accumulation of inert materials or impurities in the recycled stock. The impurities may accumulate to such a level that the process automatically comes to a stop. Yeah, so the it is one of the greatest disadvantages of the recycling operations, that is the accumulation of inert materials or impurities in the recycled stock. Since it is being partly returned to the unit again, certain materials may get accumulated, like the inert materials may get accumulated on the recycled stock. So in order to overcome this difficulty, we are doing this blowdown approach. Okay, in the steam boiler using feed water containing dissolved solids, the solids would accumulate in the boiler as steam is removed. So certain amounts of boiler contents are periodically removed as blowdown, which in principle is analogous to purging operation. So both these are analogous to each other in the principle. So if the impurities of the inert material is removed only through purge stream, then the amounts of inerts entering the fresh feed should be equal to the amount of inerts in the purge. And let P be the amount of purge and XP be the composition of inert in it, and XI be the weight of the fraction of inerts in feed. And consider this figure, and we can see that inert balance P into XP is equal to F into XI. And now finally talking about the last question and of this module, refer to the given figure. One half of the high pressure steam after being utilized for power generation is sent to the plant as process steam. The other half is returned to the boiler as condensation carrying 50 parts per million solids. To keep the solid level in the boiler below 1600 ppm solids, a part of the boiler water is blown out continuously. The fresh boiler feed water is found to contain 500 ppm solids. If steam produced is free of solids, calculate the weight ratio of feed water to the blown out water. Okay, let's take the solid balance around the boiler, that is F into 500 divided by 10 raised to 6 is plus S by 2 into 50 by 10 raised to 6 is equal to B into 1600 divided by 10 raised to 6. And the overall material balance is equal to S by 2 equal to F minus B and S equal to 2 into F minus B. And substituting for the values of value of S in equation 1, we get the equation as being written in the slide. And 500 F plus 50 F minus 50 B is equal to 1600 B. And finally, if we have 550 F is equal to 1650 B, and the answer for F by B is equal to B is equal to 3. So, that's all about this module. I hope you understood about this module. Thank you.